we looked at basic operations of functions, we were looking at really equivalents of addition, subtraction, multiplication, and division, but for functions. So we saw that because we can add, we can multiply, we can take away, and we can divide numbers, we can kind of bring those operations over to the world of functions. It's pretty simple. What you do is you just take your function, two functions, and you add the outputs. That's the sum, basically, and you multiply the outputs, dot, dot, dot. So the world of functions actually admits another operation, another way that we can combine functions to form a new function, which doesn't really have any equivalent in the world of numbers, namely composition of functions. So let me start off by kind of just explaining some important things about notation more than anything else. So composition of functions it's a difficult thing. A lot of people struggle with it for good reason. So let's take two functions, f and g. So let's just recall what the notation means. So recall. When we write down f of x, what that really means is it's the output of the function when the input is the number x. So this is a number. This is the output of the function when the input is the number x. All right. So just a super simple example. If I was to write, I don't know, we'll do f of x is equal to x cubed. So I take a number and I just multiply it by itself 3 times. So an important way to read this is as follows. So I'm not really going to do this. I'll do it a little bit during this video, but not outside of it. The way you should read this is f of the input is equal to the input, let's say to the power 3 here. So x is kind of a stand-in for the input number. And we could really use any symbol at all for it, right? We could use y even, we could choose z, we could choose anything. We could choose a Christmas tree symbol if we wanted, as long as we knew it represented a number in the domain. So this is an important thing to be aware of in terms of the notation. So here's an important comment on it. Important notational comment. So an important notational comment. So replacing, let's say x on the left hand side with some different expression. So x over here, the left hand side. Well, if I'm changing my notation for the input, I've also got to change the notation for the input on the right hand side. So this implies I would have to must replace x on the right hand side with the exact same expression. So as an example, just rotate this a little bit. So this is important, right? It's kind of it's a little bit of a subtle point. It doesn't feel terribly profound, but it's really important when it comes to what we're going to do now. So just as a quick example with this guy here, with f of x is equal to x squared. Well, if instead of x we use the notation z, well then f of z would have to be equal to z cubed. If instead of x we represented the input with 2x, Okay, well, what's in the bracket is the input. So this has to be equal to 2x to the power 3, which I suppose you could simplify using your exponent laws, x times x cubed if you wanted. Okay, f with an x plus 1 in here. Well, the x plus 1 is the input into the function f, so you've got to do the same thing on the other side. X plus 1 cubed. Now, just something to say here. Let's take a look at this example. F is your original function, okay? And I am replacing the input with slightly different notation. So if you're looking at this example, there are kind of two ways that you should think about the input. The input into f, which is this whole expression. But then you could kind of realign your thinking and say, well, actually, let's just think about x as the input to this expression. And that'll change the function, as we're going to see. But the main thing is, whatever you're going to put into your function has to be exactly the same on the other side. So it's really up here. Whatever our symbol is for the input, x plus 1, x minus 1, who knows, it's got to be exactly the same on both sides. Okay, it's a very important comment on notation. Alright, so here's the basic idea behind composition. So the basic idea of composition. Really what we're going to do is take two functions and I'm going to run both of them, and I'm going to run, I don't know, let's say the g first and then the f. So what we'll do is the following. We'll find the output of g and then use that as the input of f. As the input to f. So let me draw a picture of what I mean by that. So, picture is always a good plan, thinking about these things visually. Let's take 3 number lines. 3 number lines. So here's what I'm going to do. I'm going to take some position x, and I'm going to feed it into g. So if I feed it into g, what happens? I end up going over to some gx, don't I? So this is me feeding x into g. So this is the input into g. So then what am I going to do? Well, let's take this gx now and let's feed that into f. So it's like kind of going through 2 different machines. So feed it into f. Now where would I end up over? So if this is your f here, you would end up over at this position, which would be f with g of x fed into it. Okay, remember whatever is inside the bracket is the input into f. So this position here is kind of interesting. This position, it's kind of an input and an output, right? This is the output of g, but that's going to be the new input of f. The input of f. So what have I got here? Well, now I've constructed, if you want, a new rule, a new way of assigning an output to an input. So if I start over here, think about x as the overall input, I feed it through g, then I feed that output into f, just like we see here, and that gives me a number. F composed with g is what I'm going to call it. So overall, this defines a new function. And it's nice to kind of think about it as, I'll do it underneath, all the way across there. And I'm going to have some notation for this. I'm going to write this as f with a kind of a little circle g. So this is just notation. So this is notation. And maybe you want to say it's something like do G, then F. It's a bit strange because you might think it should be the other way around. Do F first and then G because you're reading it in that direction. But because of the way functions are written, it's more sensible to write it like this. Okay. So this is a new function. Right? I'm doing the function G and then I'm kind of running the second function F. So it's like two machines basically put together to form one. So let's write all this down carefully as a definition. Or at least let's come up with some terminology for it. So definition. So when I've got these two functions, this f circle g, we call this the composition of f and g. And the convention is when you write it like this, g is the first one to happen, followed by f. So when you write this down, you would write f circle g. X is, well, first of all, you do g, but then you feed that into f, like this. So the composite of two functions is this new function which is done by doing the first and then the second, essentially. It's a difficult idea. It doesn't have any parallel really with numbers. It doesn't really have any parallel with numbers. It's kind of its own new thing which is very specific to the world of functions. So I think it's a good idea to do some low-level examples here to make sure we really understand what's going on. So let's reach back to a simple example that we did when I was talking about kind of sums and quotients and products of functions. So example. Let's do f of x is equal to 1 over x. And let's do g of x is equal to x squared minus 1. So I think I looked at things like the sum and the quotient of these, evaluated at 2. Let's do the same thing. So imagine I want to know what the composite function is evaluated at 2. So what's this equal to? That's the question. Well, the first thing I do is g. So g of 2 is equal to 2 squared minus 1, which is equal to 4 minus 1, which is equal to 3. And then 3, the output of g becomes the input of f. So f of 3 is equal to what? It's equal to 1/3. So putting all this together tells me f composed with g 2 is equal to what? It's going to be equal to 1/3. And of course, we could write this as follows. This, by definition, is f. The g of x fed into it, or sorry, g of 2 fed into it, which is equal to f of 3. It's a slightly different way to write it down if you want. So again, let's draw 3 number lines just to make sure we really understand conceptually what's happening. Sort of I've got my point 2 as a start. Then I'm doing first function, which is g. So it's x squared minus 1. So that goes across to the point 3 here. And then I'm doing the next function, which is f, the reciprocal function, 1 over x. That sends this guy across to 1/3. Okay, so that's me doing it very specifically for one point. How would we write this down if I had a more, or how would we write down an example if I had to kind of keep things general? I don't want to have a totally separate calculation for every single potential input. So let's do one where we kind of keep it with a general input x, shall we? So let's take f of x is equal to x squared plus 2, and g of x is equal to 3x minus 1. All right. So let's really carefully unpack this. So f composed with g of x. I want to write this formula down. I don't want to just write it for a specific number. So this, of course, by definition is, well, we do gx and then we feed it into f. What's gx? Gx is equal to f. So gx is equal to 3x minus 1. Okay, so now what is this equal to? Well, now the 3x minus 1 is the input into f. So this has to be equal to 3x minus 1 all squared plus 2. Now again, let me just reiterate exactly the statement I made at the beginning. F is x squared plus 2, but a way to think about that is f of the input is equal to the input squared plus 2. So if the input is 3x minus 1, you've got to write that on both sides. Okay, so these must be exactly the same, must be completely identical. Okay, so now what? Well, now we could factor this out if we want. We don't really need to, but might as well just for fun. So this is 9x squared, it turns out, minus 6x plus 3, I think. So I get this quadratic expression. Okay, so pretty neat. The idea is fairly simple. It can be algebraically pretty confusing. But let's do the other way around. This is an interesting idea. So let's now instead think about g composed with f. Well, let's think what this would have to mean. Well, according to the notation, I'd be doing it the other way around. I'd be doing f first and then g. So I'd do f to begin with, and then I'd feed that into g. So it's kind of backwards. So let's see what happens. So this will now be g of, well, the inside is going to be x squared plus 2. And now same story as before. I need to replace the input in g with x squared plus 2. So this has to become 3 x squared plus 2 minus 1. And what does all this come out to be equal to? Well, it comes out to be equal to 3 x squared. Is it plus 6? Yes, by distributing. And then minus 1, so plus 5. So this is kind of interesting. It seems to me that these two output expressions, this and this, are different. They don't look the same. Are they the same function or not? Well, I don't think so, but let's be really careful. So to show that two functions are not equal as functions, we need to find some point where it messes up, right? Where they're not equal to each other. So let's just observe this. So observe that, well, let's feed in, I don't know, let's feed in 1 into both and see what happens. Yeah. So if I was to do this with a 1, that would be equal to 9 times 1 squared, sorry, is it minus, what's going on? Minus 6 times 1 plus 3. Yeah, is that right? So that's 9 minus 6 plus 3, that's equal to 6 overall. Okay, and if I was to compose the other way around and feed in 1, well, what has to happen here? It would be 3 times 1 squared plus 5, that's equal to 8. And those aren't equal to each other. So what does that mean? That means that these two things are not equal to each other as functions. So this implies f composed with g does not equal g composed with f as functions. Remember, two functions are equal as functions if and only if they're equal everywhere. Exactly the same domain and they're the same everywhere. It's not the case here. So not equal as functions. Interesting. So that actually is part of a general observation that if I take two functions and I compose, the order really matters. Which one you do first and second will completely dictate everything. So conclusion. Conclusion, in general, f composed with g is not equal, as I've written before. So if you want to use kind of fancy terminology, this would be saying that composition of functions is not a commutative property. The order matters. It's not like addition where a plus b is b plus a. It's very important which one goes first and which one goes second. Okay. So just something quick I'll say is if I can compose two functions, I can compose three functions. So just as a quick example, and any finite collection of functions, if I was to write f composed with g composed with h, so I've got three functions, well, what would this have to mean? So this would have to be, well, the way you essentially do it is you read it from right to left a little bit confusingly. So the first one that has to happen is h. So this would have to be equal to h first. Then that would have to be fed into g. And then that would have to be fed into f. Okay, so if you want to do it with kind of a picture, it gets out of hand real fast. But it would be this. You'd start with your x, then you would do h to get hx here. Actually, I should do it in the same color as the x. Then you do your g. So what does that give you? It gives you g with hx fed into it. So input and output switching. And then finally, you would feed this into f. So f with g with h. So it's this kind of nested, oh my goodness, collection of things. So that entire thing from beginning to end, that is the composite of these three. So all the way down here, that is what f composed with g composed with h is. So that's the basic idea behind composition of functions.